Welcome everyone to BigML's Winter 2017 release. So as usual, we've been constantly improving the BigML platform, always with an eye to making machine learning as easy and productive as possible. In fact, I was checking, and since our fall 2016 release, we've deployed to production more than 32 times for an average of about 2 deploys per week. So obviously that means there are a lot of things that we have improved. We're going to see a few of those improvements today, but the main event is our introduction of boosted trees. So what are they? Well, boosted trees are an ensemble method, and they complement the existing decision forest and random decision forest algorithms that are already in BigML. As such, they are suitable for supervised learning tasks, both classification and regression, with the added benefit that boosted trees are now BigML easy. This means that you can now be productive with boosted trees with a simple click and know that we've carefully curated this algorithm to work with mixed data types, missing data at training and prediction time, and that there will be these beautiful visualizations to help make sense of the results. Given that high-level introduction laden with technical terms as it was, there are a lot of things that we can break apart and discuss. And so to guide the conversation, there are these sort of three things that I want to cover today in introducing boosted trees. First, I'm going to give a quick introduction, or perhaps for some of you a reintroduction, to supervised learning and show you an example using just a single decision tree. This is just to make sure that everyone has the needed background information for when we really get under the hood with boosting. Then we're going to explore the motivation for ensembles so that you have a better idea of why they're important and when you should be using them. And in particular, we're going to contrast the boosted trees to the existing ensemble methods that BigML has, the decision forest and the random decision forests, so that you can have a better understanding of how they are different. And then finally, we're actually going to explore how boosting works. And this will give us a better understanding of the parameters that are available in BigML for fine-tuning these boosted trees. So to steal a quote from Lewis Carroll, let's begin at the beginning. What is supervised learning? All right, so the basic idea is that we have some tabular machine learning ready data. We refer to the columns as features. So for example, in a data set of housing data, we might have the address, the number of bedrooms, the number of bathrooms, etc. And of course, we have several examples of each of these houses, which are described by these features, one house in each row, and we refer to these rows as instances. Now, the important thing that defines this as a supervised learning task is that we are interested in predicting one of the columns in this data, perhaps the sale price of a home. We call this the label, and it is the known value. And so the learning is supervised in the sense that we are training an algorithm by giving it specific examples. Now, the only thing that separates a classification task from a regression task is the data type of the label. So if the label is a categorical, as in this example that I'm showing you here, which is a list of actions that are recommended to take when you're encountering an animal, perhaps on a safari adventure, then we refer to this as a classification, right? The actions are a list of things like run or take a picture. That's a classification problem. If, however, the label is numeric, for example, how fast you need to run from these animals in order to survive, then we will refer to this as a regression, all right? The label that we're trying to predict is a numeric value, then it's a regression. Now, this is important for boosted trees only in the sense that it changes the behavior a little, which we're going to see later on. All right, so one last concept of supervised learning that we need to mention is performing an evaluation. Now, since we have known values, again, in this case, the sale price of homes, we can split this data into a training set and a test set. So now this allows us to test the model in a meaningful way because we can see how it performs on data that it never saw during training. That is, we use one data set to create the model, and we use the other data set that it wasn't trained on to evaluate it. So we can make predictions with the model, we can compare it with the known values in this holdout or test set, and we can see exactly how well it does on new data. And this gives us some confidence in the ability of this model to make accurate predictions. Okay, so with that, let's do just a quick demo of modeling actual housing data, just using a single tree so we can make sure that all of those topics are solid. All right, so I'm going to use some data that I've collected from Redfin, and this is sale price or sales data for the city of Corvallis over the last year or so. And Corvallis is the city where I'm broadcasting from right now. And I've cleaned it up a little bit so it just has the fields we're interested in. So you can see, just like in the slides, we have things like the address, the number of bedrooms and the bathrooms, And the thing that we're going to be interested in predicting is this last sale price. So now that I have this source loaded, I'm going to go ahead and do our one-click data set so that we can get our summary statistics and make sure that everything looks okay. And in particular, at this step, because I want to be able to compare the single model with the ensemble methods, I want to do that training and test split that we were talking about. So let's go ahead and do a training and test split, and we'll take the default of 80-20, and I'm going to use a seed just to make sure that we get repeatable results. All right, so now if I were to go back to my data set view, I have 3 data sets. I have the original, and then I have 2 orthogonal subsets, one at 80% and one at 20%. Now I'm going to do one additional little trick here, which is that because the field I'm interested in predicting isn't the last column of the data set, I'm actually just going to hit this pencil and set this as the default objective field. This will save me from myself during the demo from forgetting to set the objective that I want to predict and accidentally predicting the longitude. Can't imagine how many times I've done that. So we'll go ahead and set that, and now this is the default objective. Okay, with all that, all we need to do for this 80% is just hit one-click model, and this is going to give us this a decision tree that will be able to predict the sale price of a home in the Corvallis market based on the features of the home. And it won't surprise you to know that this matches our intuition anyways, that the square footage ends up at the root of this tree. That seems fairly reasonable. And we get these nice splits where the square footage is bounded in a certain range. We have a certain number of bathrooms. It's interesting that latitude is important, and actually the way you would know that unless you live here, but Corvallis is structured so that houses further north tend to be larger and more expensive, and houses further south are in a flat area of town where construction is very easy and the sale prices tend to be lower. But we can also see that the year built and the size of the lots is also impacting the sale price. And now, of course, just like before, there's nothing new in this sense. We could use this model to make predictions, and we could put new homes in here and get a sense of how much we think they're going to sell for. But let's go ahead and evaluate this just so we can get a baseline performance for a single tree on how well we can do at predicting these home prices. Now, because this is a regression, we're predicting the sale price of home, a real value number. The metrics we're going to get are the mean absolute error, the mean squared error, and the R squared. And for the purposes of today, we're going to focus on seeing if we can improve this R squared. So this model, as is, comes up with an R squared of 0.52, which is not bad, but it's not particularly great either. We'd like this to be as close to 1 as we can get it. That's how you play with the R squared. The closer you are to 1, the better you're doing. And so we're going to be, in the ensemble methods, we're going to be seeing if we can raise that up a little bit. If you've done a lot of this model building and evaluations, you might be looking at that and going, wow, an R squared of 0.52, that's really bad. But keep in mind that this is one very small data set. We only have, I forget, maybe a few hundred rows maximum. And we have a lot of features that can actually be improved. So this is just a very small and simple demo. So don't get too obsessed about the absolute value of this R squared. This is just our baseline. We're going to see if we can do better. So we took our housing data, we created this model, and now we want to use it to make predictions, but our evaluation is showing us that this model is not performing very well. One thing we can try to do better is, of course, an ensemble. And I think it's really helpful to understand why an ensemble might do better. And in order to do that, we need to figure out what it is about just doing a single decision tree that could go wrong. I mean, why, if we run another decision tree, will it do better? It might. And if I run another one, it might do a little bit different. They'll probably all do roughly the same. But what is it that keeps them from being the best they can be, if you will? We're going to break this down to sort of 4 possible problems and some intuition that is going to lead us to why an ensemble might work better. All right, so first, a single tree can overfit, especially if there are outliers. And in the case of this housing data, it's easy to imagine that there are a large number of these normal size homes, right? Homes that your average family lives in, whose price relates to square footage very reasonably. But once a house becomes very large, like a mansion, the prices behave much differently. They typically increase very rapidly. Those are essentially outliers from the norm. And now, while that is the nature of this housing data, if we were mostly interested in making predictions for family homes, having a few mansions in your data is going to skew this model. Now, for example, we could deal with the outliers very easily by just filtering out the mansions. But the important thing here is that this can happen in more subtle ways. You can have these outliers that are much harder to detect. And the single model is going to try to account for these outliers. It's going to try to make them fit into the model. And so our ensemble intuition is that, instead of building a single model, we could just build lots of models. And the way that we'll make them different is that we'll build each one with only some of the data. This essentially has the effect of averaging out the outliers. So another way that single models can fail is that they can underfit, especially if there's not enough training data to discover a single good representation. So now try to imagine that in our housing data, we just don't have any homes that are between 1,000 and 2,000 square feet by bad luck. We made a bad sample, or we didn't collect good enough data. So it's a very important part of our data set, and we just don't have enough data there. Now it's likely that the model will not be able to make good predictions for homes in this range because it has lots of samples for homes that are smaller, it has lots of samples for homes that are larger, and there are just too many possible solutions, right, for the homes between 1,000 and 2,000 square feet. We don't have enough data there. So if we try to build a model, the model will be happy to make predictions in that region, but they just may not perform very well. And once again, our ensemble intuition is that, okay, well, rather than just rely on a single guess, if we build multiple models and combine their predictions, this is going to give us sort of an average of this expected behavior in this region where we don't have enough data. And this helps us avoid the risk of picking just one possibly bad solution, right? We get a bit more fairness. Now, another possibility is that the data is just far too complicated for the model to represent at all. So don't think about trees. Try to imagine that we were just trying to fit a line to the relationship between square foot and price of a home. This would probably fit badly because a line is not going to accurately model the nearly exponential price increase that you see when you start looking at mansions. Okay, the line just isn't going to fit with those outliers in there. The line is not complicated enough algorithm for the data. So to work around this again, though, we could just build multiple models, many models, again, sampling different parts of the data. Because we're training each model on some of the data, each model is in some sense becoming a limited expert on just that part. And this allows the final ensemble of all these models to express much more complexity than a single model could. Now, this is much more subtle when we're talking about trees, which are already very good with dealing complexity, but it still applies. You can have very, very complicated data that a single tree just isn't quite cutting it. And by having multiple trees, you're actually increasing the complexity that you can solve. The final thing is that these machine learning models, they often rely on some kind of stochastic process, and it's possible to just get an unlucky solution. So once again, by building many models, we can mitigate this risk, since it's really unlikely that every model is going to be unlucky. All right, so by building a bunch, we sort of eliminate or reduce the possibility of just having bad initial conditions. Okay, now in all of these cases, the basic idea is to just build an ensemble of models. And since in this case, each model is a tree, it's common to refer to this ensemble of trees as a forest. So let's take a look at a simple decision forest. Now, the basic idea is to build our ensemble of models by making each one different by training on some random sample of the data. So I'm going to take my data set, and for the first one, I'm going to just take some of the rows, right? So here I've taken 3 of those 6 rows randomly to build my first sample, and I use that sample to build my first model. And then I take a different sample, different rows now, and I build a second model. And I just do this again and again. And in this case, I'm only showing 4, but you could imagine this could be 10, 100, or 1,000 times. We're just going to take all these random samples and build separate models. Now, when it's time to make a prediction, we don't have one prediction anymore. We're going to end up with a whole family of predictions, one for each model. And so we need to combine them together into a final prediction. And in this case, since we're talking about regression, you could, of course, do this just with an average. If this was a classification problem, we would need to apply some kind of voting algorithm, maybe majority wins, or we could weight by confidence, etc. All right, but we need to take, each tree is going to make a prediction for new data, and then we need to combine those predictions together. By the way, this is often also known as bagging, this particular decision forest. So let's do a quick example of this. And this is something that's been in BigML for a while, but the way that you configure it has changed a little bit, so it won't hurt to review it. And again, it's nice to be able to compare with the boosting when we introduce that. So we're going to take our training set again, and now instead of configuring a model, we're just going to go ahead and configure an ensemble. And you can see that there's a type of algorithm to choose here, and we're just going to take the default of decision forest. And you can see that we can also specify the number of models we'd like. The default is 10. We can, of course, dial that all the way up to, say, 1,000. But for this simple example, we'll just go ahead and take the default at 10. And there's an advanced configuration panel that we're going to get into on the next demo, so I won't show that to you yet. We'll just go ahead and take the default settings. Now remember, this is going to build us 10 trees, each tree built with this random sample of our pricing data. And so we're going to end up with 10 models on the output. Now 10 models is kind of hard to look at. You actually can do it. There's this button here which will show you the model list. and you can actually see pictorially, this is actually a picture of each tree. You can see exactly what they look like. You can interact with these trees individually, but it's becoming less useful to visualize this way because the trees are built with this random sample, and so it's not necessarily clear what you're looking at anymore as you look at each one of these trees. You've got rules that are discovered, but for only some of your data. And because of that, we now provide the partial dependency plot by default. And this allows you to see the performance of the ensemble in 2 dimensions. All right, so I can see that on the X coordinate here, I've got the square footage, and the Y coordinate, I have the lot size. And the coloration is by the predicted outcome. So these sort of light blue areas are low home prices. Okay, you can see in the upper right there, the prediction is around 200,000 or so. And this lighter green color is a much higher predicted sale price of closer to 700,000. And so we can kind of see how the decision boundary is developing as we go across the square footage, right? The prices are increasing. And for a small square footage, the size of the lot is not very important. But as the square footage increases, the size of the lot does start becoming important. We can see that anything over 200,000 square feet on the lot size starts becoming quite a factor in the price, jumping it from just under 500 up to more than 600,000 on this little boundary right here. Okay, now of course we can change this. If we wanted to see the square footage versus the latitude or something, we can change that so we can see how the home prices are changing with respect to latitude. And if we want to see how the decision boundary is changing with respect to the other variables, we can do that as well. So now we can take the other input fields and we can say what happens if for this same setup here we have nearly 5 bedrooms, and you can see how the pricing has changed over these 2 dimensions, right? If I go way down to less than 1 bathroom, I can see how the pricing information is changing. All right. And one additional thing that I'll point out, right now we're seeing all 10 trees, but we can actually dial this down if we just want to see 1 tree at a time. This is going to be more useful later. But now of the 10 trees, we're just visualizing the PDP for 1 of them. And if I click this button in the upper right here, it's sampling a different tree and then a different tree, or I can kind of blend these a little bit. If I want to see what it looks like with 7 trees, I can do that as well, etc. All right, now of course we could use this ensemble to make a prediction. We could put new data in and we would get a vote from each tree. They would give us a prediction of the sale price, and we could actually then look at the final prediction, considering the prediction from each tree. But let's go ahead and just do the evaluation. So we'll go back to our ensemble, and we'll evaluate this guy. The same 20%. And again, I'm going to take the defaults. All right, and now we can look at our R squared. So we had a 0.52 before, and you can see that it's gone up to a 0.67. This is a pretty significant gain by, well, essentially doing nothing, right? I just changed from configuring a model to doing an ensemble. I didn't even change any of the default parameters for the ensemble. Now, this trick of building an ensemble by sampling the data for each model can be extended. So instead of just sampling rows like we did the first time, we can actually choose the features that we want to use for the splits randomly as well. Okay, now you can think of this as sampling both the rows and the columns. So each model is being built with sort of this random subset of rows and columns, but otherwise it progresses the same. I take this sample, I build a model, I get a different sample of rows and columns, I build a model. Now that's not strictly right, because what's happening is we're actually resampling the columns at each split. So as the tree goes down, it tries to make a decision about the next split, and it chooses the columns randomly. So the sampling is done a little differently. But for visualization, this gives you the sense that we're getting just randomization in 2 dimensions. And this is a very powerful technique that's often referred to as a random decision forest. Now, we have the same thing at prediction time. We're going to get multiple predictions, and we need to combine them together to get a final prediction, but otherwise it works basically the same. Now, this is something that has been in BigML for quite some time, but the way that you configure it has changed. So let's take a quick look at that as well. So we'll take our training set again. We'll come back into the configure ensemble. We're still going to do a decision forest, and we'll still stay at 10, but now we need to go into the advanced configuration panel, and in here there's a sub panel for configuring the trees. And this is where you're going to find the advanced settings. In particular, this is your missing splits, where if we wanted each tree to learn from missing data, all right, to consider missing values to somehow be important. We can also configure the node threshold. We're going to mention this again, so that it's important to remember that it's here. I can dial this up, and this will allow each individual tree in the ensemble to become more complex, if you will. It allows each tree to have more nodes. You could, of course, by a similar measure, you could say, no, I want each tree to be much simpler. I want to build a large ensemble of very simple trees. Okay, so we could do that as well. For this, let's just go ahead and keep the default 512. But the important setting in this tree configuration panel is this randomize parameter. By turning this on, we're going to randomly select the subset of fields at each split. So this is going to give us that random decision forest. And there's one additional criteria we can specify, which is how many random candidates to use. So the default, I believe, it uses the square root. So if we had 100 features at each split, it's only going to take 10. But you can also make a hard limit here if you only want to say, look, you can only have 5 randomly selected features at each split. You could do that as well. Now let's go ahead and take the default. So this is going to give us our random decision forest with 10 trees and the default settings. So we'll go ahead and create this ensemble, and then we'll be able to evaluate it and compare it to the single tree and to the bagging decision forest. All right, now the same as before, we get the PDP visualization so that we can interact with this ensemble and see how it's making predictions. And let's go ahead and run the evaluation. So the same test set. All right, and now we see R squared. Now this, I get a little bit different answer every time, but in general, it is lower, and that's okay. The random decision forest, this is, again, remember, this is a really small data set. It doesn't have that many features. It doesn't even have that many rows. And by adding the randomization in the feature selection, in some way, we're sort of making this ensemble too complicated for such simple data, and it's actually performing a little bit worse. That's not an uncommon thing when you have these really simple data sets. A particular case where random decision forests are really great is when you have really wide data sets. If you have 10,000 features, that is something where a single tree struggles to do this computation well because it has so many features to choose from and there's a lot of extra computation. Whereas a random decision forest, each tree can be built in parallel and taking random samples of those features, and you tend to get a little better performance. All right, it's a little hand wavy, but again, it's okay that this is low for this data set. This is mostly just because we've now made an ensemble that's really powerful for what is essentially a much simpler data set. So, but this does give us at least some metric. And generally in the experimentation, this is normally better than a single tree, but actually not as good as the bagging. This particular data set works very well with the basic decision forest. So now let's boost this topic. So consider this. Instead of these sampling tricks to build an ensemble, can we incrementally improve a single model? That is, if you think about the decision forest, each tree is kind of starting from the same conditions, right? It's taking some kind of a sample, it's building a tree, and getting a result. And the next tree is starting all over again. It doesn't learn from the other trees at all. So is there some way that we can just build one tree and then go, you know what, can we just make that tree a little better? And then perhaps make it a little better again. And the intuition here is that the training data has the correct answer. Right? Remember, this is supervised learning, so we know what the answer should have been. And now the idea is, well, can we just model the errors? And well, of course we can. So, but the basic idea here is we're going to take the data set, we've got our label, we use that to build a model, we could run some kind of a batch prediction, and we could take all of those predicted outcomes and put them back into the data set. So imagine I just append the predicted column to my data set. Well, now for each row in this data set, I know what it was supposed to be, and I know what the model predicted. That means I could make a new data set that predicts the error, right? Remember, we're thinking of regressions here, so we could just think of the error as the difference, if you like. You could do the square error or something, but for now, let's just imagine that we subtract them. All right, so I could just make a new column on there that says, you know what, it was supposed to be 100, you said 200, you're off by 100. To see this idea a little more concretely, let's consider the housing data again. So we're going to take this data of sold homes, and we're going to build a model which predicts the sale price. And then for each home in the training data, we'll use the model to make a prediction. So we can see that for the first home, the real sale price was $360,000, and this model predicted a sale price of $360,750. So it made an error of 750, or you could say negative 750. I couldn't decide when I was making the slide, but it's off by 750. And what we can do is we can take that error and we can just glue it back onto the original data set. So now I have a data set that's comprised of features describing each house and how much error I made in the first model. And I can use this to build a new model. Well, what am I modeling? I'm essentially modeling the expected error. All right. When I see this kind of a home, I think the first model is going to make this much error. Well, this means that the predicted outcomes are going to be error predictions. The data I'm showing you is actually real data. What I previously, on the previous slide, I built the model, I did a batch prediction, I appended the data set, I built another model. This is actually what happened for that $360,000 house. The first model predicted 360,750, and when I made a new data set with the error, the second model for that home predicted an error of 750. And so you can kind of see that if we now combine these models, we would get we would get an exact answer for the first home. We would know that model 1 predicted 360,750 and model 2 predicted an error of 750, and we would just subtract those and we would get the correct answer of 360,000. Now, of course, in home 4, we actually do a little worse, but that's okay, or a 3. And now if it helps conceptually, this is kind of like playing this game. Hey, model 1, what do you predict is the sale price of this home? And then you say, you know what, model 2, how much error do you think that model 1 just made? All right, and then you're going to take both of those opinions and put them together into a final answer. But why stop at one iteration, right? We could keep going. We could make a new model that predicts the error of model 2, etc. So that's what we're going to do. This is now defining boosting. So at iteration 1, we're going to take our data set and we're going to build a model. And we're going to use that model to make a new data set, essentially, that contains all of the errors that the first model made. And then we can use that data set to make a new model 2. And we'll use that model to make a new data set of errors that model 2 made. And in iteration 3, we'll use that data set to build a new model. And we'll use that model to compute all the errors that we made, and et cetera, et cetera, et cetera. We just keep going as far as we like, or until we have some kind of stopping criteria that says, this is approved enough, or I just want to stop at 10 or 50. Okay, we'll see examples doing that, but otherwise we can continue for as many as we like. Now, at prediction time, we're once again going to have multiple predictions, one from each model, but this time the trees don't vote and we don't take an average or anything, because each tree is making a sort of like a complementary prediction, right? And so what happens is instead you essentially add them together. You're going to take the first prediction and correct it by the error predicted by the second one, correct that by the error predicted by the third, and correct it by the error predicted by the fourth. But it's the same basic idea. We're applying some kind of a function to these family of predictions to get our final prediction. Now, the way that I just explained this is not exactly the way the BigML platform is performing boosting. In particular, by default, the BigML implementation also randomly samples the rows in each model. And this helps reduce the likelihood of overfitting. So the correct picture would look a bit more like this. Each of those subsequent trees is actually being built with a random sample, as well as in the decision forest case. Unfortunately, you don't have to manually perform all these steps. You can make a boosted tree ensemble very easily. And so let's go ahead and do that. So we'll take our training data set at 80%, and we'll go back into the configure ensemble. And now instead of a decision forest, we want to do boosted trees. And the first thing you'll notice is that number of models has been grayed out and number of iterations has been turned on. So what is the difference here? Well, number of iterations is going to behave somewhat like number of models. Okay, it's some kind of a guide as to how complex this ensemble is going to be. But it isn't that if we set this to 10, you're necessarily going to get 10 models. You might actually get less than 10 models, and you might actually get more than 10 models. And I'll explain later on how that can actually happen. But this is basically a guideline. You can think of this as how many models you're going to get, okay, but it isn't exactly. It's the number of iterations that we're going to perform that I was showing in that slide before. And now you'll notice that there's a new subpanel down here called boosting, where we have some configuration options that we can change. And I'm going to drill in and explain these very detailed, but basically the default is something called early out of bag, and this allows the boosting algorithm to stop when it thinks it's doing well enough. And we also have a learning rate, which sort of defines how aggressive it is at predicting the error of each step, if you will. Okay, but let's go ahead and take the defaults for this. So we're going to do just a 10 iteration boosted tree with all of the defaults. So we'll create that ensemble. And actually, while that's building, I'm going to go ahead and create a couple of more. So we'll take this 80% and we'll configure another ensemble. And we'll do this one also boosted, but for this one, I'm going to let it do 50 iterations and otherwise the defaults. And we'll do another one at 100. So configure the ensemble, boosted trees, and we'll do 100 iterations for this one. All right, so now we'll have these three that we can compare. So let's take a look at the first one, which should be this one. All right, we can see that randomize is no, which I'll explain. So we have boosted trees. There is 10 models. Okay, we did 10 iterations and we actually did end up with 10 models. And for the most part, it looks exactly the same like the other ensemble methods, right? We've built these 10 trees and we can see their performance in the PDP. But now you'll notice that we don't give you the option to see these trees individually. And that's because at this stage, we've really lost meaning of what those trees mean. I mean, the 10th tree in this ensemble is predicting the error of the 9th tree. Examining that tree individually without being part of the ensemble would be really non-interpretable. And so for this situation, having the PDP is essential. This is actually giving you a very good insight into what this ensemble is doing. And we can play the same trick we did before. We can sample a subset of these models and see what the performance looks like, or we can use the entire set of models that were built for this boosted ensemble. All right, so let's go ahead and evaluate this and see how well it performs. All right, and you can see that we got an R squared of 0.62, which I believe is right around the same value that we got for the decision force. It may have been a 0.64 if I remember correctly, although we can just double check on the evaluations. This should show us. So we got a 0.52 for the single tree. We actually got a 0.67 and then a 0.49, and then the single boosted ensemble gave us a 0.62. All right, we can see all of those measurements there. Now, don't worry, we're going to improve that, you'll see. So let's come back to our second ensemble that had 50 iterations. So this is now the boosted ensemble with 50 iterations. And you notice that there's 50 models. All right, so it built all 50 models. And we can try evaluating this one now, but of course we can see if this looks any different, just out of curiosity. It does look a little different, but let's go ahead and evaluate this guy. All right, and now the R squared went down. Isn't that odd? But it isn't, don't worry. So we actually got a lower R squared there, but we'll come back and let's take a look at the 100. Okay, and now this is interesting. For this one, we set the iterations at 100, remember? So if I go into the details, oh, we don't show it there, but that's all right. This is the last ensemble we did that had the iterations set to 100. But what you'll notice looking at it is that it only built 45 models. And isn't that a little odd that when we did the 50 iterations, we got 50 models, and we did 100 iterations, we ended up with 45 models. That seems odd. Let's go ahead and evaluate this so we can see how this one performed. And actually we got a lower R squared. Well, that can happen. Random processes can bite you. All right. Well, if we do this, we'll give it one more try just to see if I got a very unlucky situation. And I'll show you. Let's see. So we'll do the 100 iterations. So we'll let that run. But while that's running, actually, let me show you the ensembles that we show have similar information that were available before. Okay, so you can see an ensemble summary report. So you can see an indication of how important each field was in the final outcome, right, in reducing the error, essentially, of the final outcome. So we can see that the square footage is a very dominant feature in predicting the home price, as is actually the address, which makes sense. And the latitude, again, Corvallis is structured where the homes towards the north tend to be more expensive. And the year built, which also matches our intuition, right? We expect this to at least have some contribution, but we can see in a relative scale how important each one of these features was in predicting the sale price. Of course, like everything else in BigML, these boosted trees are fully actionable, all right? So if I want to run this now in Python, I can use this boosted ensemble in Python and make predictions. And you could, of course, do this with local predictions as well. So you can instantiate this as a class in Python, which has a predict method, and you can make predictions with your boosted ensemble completely disconnected from the API, right? This entire boosted ensemble is completely extractable from the platform, just like everything else. So what about these boosting parameters? So the first is this number of iterations. And again, this is sort of similar to the number of models that you're going to get for decision forest or random decision forest, except that it isn't exactly the number of models, right? But it's a similar idea. It's giving you some measure of the complexity. And the caveat here is that the iterations can be limited with this early stopping criteria, which is actually what's biting me right now. And I'm going to explain that a little bit better. But the first is this early out of bag. And what this does is that at each iteration, it tests with the out of bag samples. What does that mean? Well, remember, this is our construction for how we're doing boosting. And at iteration 2, when we're building that model, we can do sort of like a little mini evaluation using all of the rows that we didn't use to build the model. That's the out of bag sample, all the ones that weren't selected to build the model. And then we can actually make a quick measurement of how much the ensemble is improving. And if it isn't improving enough, if it's just improving a tiny little bit, then maybe we're done. And so then we can tell the algorithm to stop there. It doesn't need to build any more trees. Okay, we can do a similar thing with something called early holdout. But what's going to happen with this is that it's going to hold out a fixed set of rows at the first iteration, and it's going to use that same set at every iteration to evaluate the performance, rather than trying to use the out of bag sample. The thing about that is that it can actually be a little bit slower, because once it picks the number of iterations, it goes back and starts over using all of the rows. So it's going to essentially do twice as many iterations. And then you can also choose to do none, and this will just always perform the all iterations. So if I say do 1,000 iterations and don't use an early stopping criteria, it's going to go ahead and build all 1,000 trees. Now, in general, it's better to use a high number of iterations and let the early stopping do its work. And this is what I was trying to demonstrate, but it wasn't cooperating today. But here's the basic idea when you're building these ensembles. There's a bit of randomness in how the trees are progressing, right? This is a stochastic process. And the early stopping criteria is going along, and as it's progressing, it's measuring how much improvement each iteration is making. And when that improvement is small enough, it's essentially converged, if you will. And we know that that ensemble is doing probably the best that it's going to do. Because this is a somewhat random process, how many iterations that is going to change, or may change every time, depending on your data. For the data I'm showing you right now, it changes pretty significantly. And so what I mean is that if you set the number of iterations to 50, and the algorithm detects that at iteration 43 it's doing well enough, and it stops, well, that's going to be okay, all right? Because the early stop means that the iterative improvement, the improvement at each iteration, is small, and so it's essentially converged before being forcibly stopped. But contrarily, if the algorithm was let to run long enough and it would have stopped at 49, but we told it, look, only do 10 iterations, then this is not going to work out well, because this hard limit on the iterations has stopped improving the quality of this boosting long before there was enough iterations to achieve essentially the best quality. And so, at least in my experience in playing with boosting, it's been best to set the iterations high and then allow that early stop criteria to save you from the extra computation. Now, the learning rate, this is going to control how aggressively boosting is going to fit the data. So internally, the boosting algorithm is a variant of gradient boosting. And one of the parameters in all gradient type algorithms is the step size, essentially how far to move towards the local minimum with each iteration. Now, that step size is computed using both an internal estimate and this learning rate. So in general, a large learning rate will converge faster, but there's a risk of overfitting. However, you have to keep in mind that if the learning rate is too high, then it's possible that your step will overshoot these local minimums, and this is actually going to make convergence slower, if not potentially impossible. And so playing with the learning rate is kind of one of those things that you would do if you're just really interested in turning the knobs and seeing if you can change the performance of the behavior. But in general, the default setting is probably your friend. Now, by default, as I mentioned, the boosting is going to use sampling with replacement for each tree. All right, so it's doing the same random subsamples of the features. But it turns out you can actually add the feature randomization just like in the random decision forest. So that would have the effect in this setup of randomizing the features, just like the random decision forest in the boosting algorithm. And there's no reason that you can't experiment with this if you have a sufficiently complex problem that you're trying to solve and you want to add this additional randomization. You can just turn it on right in the ensemble configuration. We can come in and say configure ensemble. We switch this to boosting. We have the settings here, but if you go back into the tree settings, you can just turn randomize on there as well. And now you can do this boosting, but with the randomizing in the feature selection of the trees as well. All right, that's a perfectly valid thing to try. Other than that, all the other tree-based options are the same, right? We can add weights for unbalanced classes. We can add the missing split feature if we want to learn from missing data. We can set a node threshold to allow for deeper trees, etc. Okay, this is all awesome. Everything's great, right? But wait a second. All of the examples I've been doing so far have been regressions. What about classification? Well, there's a little problem. So imagine that we were looking at this diabetes data set where we have this is actually from the UCI diabetes data set. We have these diagnostic measurements like the number of times the patient's been pregnant, their 2-hour plasma glucose, et cetera. And we have the label in our data set is a categorical value, which is true or false. Does this patient have diabetes or not? Nothing's wrong so far. We could use this to build a model that for each patient predicts whether or not they have diabetes. So maybe we get this outcome, right? The first patient was true, we predicted true. The second patient was false, we predicted true. True, false, false, false. Okay, so we made some mistakes. But now is when we run into the problem. How do we measure the error? What is the numeric value of saying something was true, but it was actually false? Now, of course, for a binary classifier like this, we could perhaps try calling false a 0 and true a 1, and we could just compute the error as an integer in that way, right? So now it's quite straightforward. We take 1, subtract 1, the error was 0. We have a 0 and a 1, the error is a 1. We could even take absolute values if we like, and that would probably work. But what if there are more than 2 classes? Imagine, if you will, that somehow we took this data set and from these measurements that we wanted to try to predict your favorite color, right? Red, green, or blue. So that first patient's favorite color is red, the second patient's favorite color is green. So now we have 3 classes. And when we build our model, for the first patient, we predict blue. For the second patient, we got right, we predicted green. The idea here is that in this list of possible values, red, green, and blue, how much worse is a prediction of red than green if the answer is actually supposed to be blue, right? How do we compute this in a numeric sense so that we can do the same error estimation that we were doing before? So, and the answer is to don't do that. What we're going to do is consider each class separately. So first we would build a model that predicts red versus not red, all right? And we can think of this prediction as now a probability. So for the first patient, their favorite color was red. We ended up predicting red with a very high probability, so maybe a 0.9 or something. And now the errors are very straightforward to compute because we're thinking in terms of probabilities, which range from 0 to 1. And we're essentially making this a binary class problem by doing one class versus all of the rest of the classes. Now, of course, we have to do this again. We have to now build a new model that's blue, not blue, and we of course would have to then compute all the probabilities for class blue and look at the errors again and repeat for each class at each iteration. That's all in iteration 1. We got to build that whole family of models. In iteration 2, we now have to take just one of those at a time. In this case, we're doing the red, and we're saying, okay, now we're going to build a model that predicts for the error that model 1 made in predicting the probability of red, not red. All right, and then we're going to get the predicted error for that one class, and then we have to repeat for each class again at each iteration. If that didn't make any sense, we can see it a little more graphically, a little more visually here. We're going to take our data set at iteration 1, and we're going to build a whole family of models, one per class. Each one is measuring essentially the probability of this class versus the rest. And then we're going to use that whole family of models to essentially build a new family of amended data sets that have the error that each one of those models made. And then for those, we're going to build a new family of models that predict the errors of each of the models in the first step. But otherwise, it progresses exactly the same. We build a new set of data sets that have the error for models 2, a new set of models, a new set of errors, a new set of models, etc. So the only thing that's changing is that we have to model this per class. All right, now prediction time, of course, we're going to get a whole big family of predictions, but otherwise it works roughly the same. We have to be a little bit fancier about how we combine them. There's a special function you put them in so that we end up with a nice probability per class where they all add up to 1, right, to be official probabilities. We have a little trick we have to play in the calculation there, but the basic idea is the same. We're taking all these individual predictions and then combining them together into our final prediction. So let's take a quick example of doing that, and we'll actually do this diabetes data set. All right, so as promised, this has the diagnostic information, and we have this categorical value, true or false, at the end. All right, and now we're going to configure our ensemble. We'll do boosted trees, and for this, we'll just go ahead and again take the defaults. All right, now the default is to do 10 iterations, and once this boosted ensemble comes up, what we're going to see is that it actually built 20 models. And again, this is because this is a binary class. And so at each iteration, it's essentially making 2 models. So it went, I told it 10 iterations, it did all 10, it didn't stop early, and it built 2 models at each iteration, so we end up with 20 models. Now this is important to keep in mind if you're working with a categorical value that has a high number of classes, all right, like 100 categories, then your 10 iterations might build 1,000 trees, right? Or if it had 1,000 classes and you set it to 1,000 iterations, it might build 1,000,000 trees. All right, so this sort of greatly multiplies the number of trees that are being built in this algorithm. Okay, but the same as before, we get the PDP, which gives us this very nice visualization of the decision boundary. I can dial this up so that we can see all 20 models, and we can see in this lower left-hand corner, these are all predictions of not having diabetes, right? Diabetes false with a high probability. And the upper right, where the 2-hour plasma glucose and the BMI are both high, all right? These are typically strong indicators for diabetes. We can see a high probability of diabetes being true. And we can see very visually this nice decision boundary where this ensemble is switching from a prediction of false to a prediction of true based on this diagonal representation, right? So if your BMI is very low, you can basically sustain a much higher 2-hour plasma glucose before the model is predicting that you're definitely going to have diabetes. Whereas if your BMI is super high, then even having a reasonably high 2-hour plasma glucose is pushing you into the risk zone for diabetes, if you will. Okay, so that's boosting. And of course, like everything else in BigML, it's not only easy to use, but easy to automate. So as always, we brought these boosted trees to the API first. Okay, so you can, everything that I've been showing you in this demo, you can do programmatically through the API, and the documentation is all online. And of course, it's available in the bindings as well. So you can create these boosted ensembles in, for example, I'm showing here in Python. It's very easy. You can just pass the parameters for boosting that will enable it. And you can specify the number of iterations and the early stopping criteria and all the rest of that. And of course, you can do this in WisML as well. You can just, when you create an ensemble, you can pass it the same parameters, what you want to use for boosting, and it will make your boosted trees. So now that we're adding this new boosted algorithm to sort of complement the decision forest and random decision forest we had before, how do you know which one will work the best? You know, what do you want to try? Which one are you going to do? You're going to upload your data. You want to, you know, predict churn or fraud or something. Which algorithm you're going to use? And the answer is the one that works the best. Now I know that seems like a little bit of a cop-out, but no, seriously, did you evaluate? I mean, that's really kind of the game here. You've got a couple of different ways. I mean, if you're doing a classification problem, you could even try a logistic regression if you like. But realistically, it just depends on your goals. If you have a certain goal and boosted trees work better than the decision forest in attaining that goal, that's perfectly valid. That's not, there's nothing wrong with choosing the algorithm based on the performance that you get. Right? That's a perfectly valid assertion. And that's actually why we provide this small set of these algorithms that do tend to perform a little bit differently on different types of data. And it gives you a little bit of flexibility in choosing without losing all the other things that we look for when we implement these algorithms in terms of robustness, the ability to work with missing data, the ability to be visualized and interpreted, and the ability to be automated and pulled out of the platform and used locally in an edge location. But that's a little bit of a cop-out, even I'll admit. So let me just give you like a high-level kind of picture to sort of direct you to the choice you might make depending on your data. All right, so if you have really large or complex data sets, and complexity is hard to define, but you know, you might think like a really, well, it's hard to define. You know, using a decision forest or a random decision forest, that's fine. If you have a large or complex data set, you might get better performance if you use that deeper node threshold, to give each individual tree a little more flexibility. Or if you don't want to use a deeper node threshold, then when you're using the forest, random decision forest, allowing more trees. Okay, so either one of those you can think about kind of like you're making it wider or deeper, right? That's going to help solve problems where you have these larger or complex data sets. But even better is now you can use boosting and just allow it to use more iterations. This is actually, boosting is much better at modeling this large complexity, right? Because it's essentially zeroing in on a best solution, whereas the decision forest and random decision forest are a bit more of a scattergun approach, if you will. I mean, that's awfully hand wavy, but that's basically the idea. If you have really noisy data, okay, then boosting might suffer. Okay, it's because it's trying to fine tune on a sort of local minimum or a best solution. If you've got a lot of noise, it might focus too much on that noise. And this is a case where a random decision forest is typically preferred. It's going to give you a better response when you have lots of noisy data. If you have really, really wide data, tens of thousands or hundreds of thousands of features, this is a situation where using the randomized features will be quicker. Now, keep in mind that you can do this with a decision forest and with boosting. You can turn on that randomization. And basically, this is just allowing your ensemble to be built with random subsets of the features, and that will make it perform much quicker. For your everyday, regular, easy data, okay, small data sets, a handful of features, a single model may be fine, and there's absolutely nothing wrong with that. These ensemble methods are meant to give you better performance when things get difficult, and single models have lots of other advantages, like their interpretability is much, much higher. Right? It's very easy to look at a single tree and understand exactly how it's making its decisions. For a classification that has a large number of classes, like 100 classes or 1,000 classes, keep in mind that boosting may be slower, right? Because you got that kind of multiplier. If you ask for 1,000 iterations and 1,000 classes, you could end up with 1,000,000 trees. Okay, so it might run slower, but also because it's running serially. All right, the problem with, or that's not really a problem, but the results at iteration 4 can't be computed until iteration 3 is done. Whereas if I ask for an ensemble, a decision forest, a random decision forest of 100 trees, those 100 trees can actually all be built in parallel. They don't have any codependence, right? Each one is just built with a random sample, and off you go. But with boosting, you got to do it serially. Okay, for general data, just your general run-of-the-mill data, a little bit of complexity, but not too much. Decision forest and random decision forest is likely better than a single model, or actually even boosting. This is, highly hand-wavy and dependent. But again, boosting is going to be slower since these models are processed serially, or maybe slower, right? You might get lucky and have an early stop.